Laid the foundation of probability yesterday. We did a lot of sample space things yesterday. We're going to talk about Venn diagrams today. Venn diagrams are going to help us to be, help us to see kind of these things and help us to get answers and things as we're going along. All right. Now, if I say the word complement, all right, or if I talk to you about maybe complementary angles, you did that in geometry. What's complementary angles? You remember that?
Equal?
No. They're equal to
Each other.
not the 90, yeah. So complement were two angles added up to be 90. Supplement were two angles added up to be 180. Well, if we're talking about complementary events for probability, they're going to add up to be the whole thing, one whole. All right, so 100% or one whole. All right. There's a lot of people that go, man, 60% chance of rain today. And then there's other people that go, no, there's 40% chance that it's not going to rain today, all right? Those are complement events, all right? If I have one and then the other, that's a not. So here's what we have. The probability of the event, all right, plus the probability of not the event, all right, then that equals one whole. That equals everything, okay? You can move it around and say 1 minus the event gives me not the event. All right. If you notice here, the symbol, if we have an apostrophe, the apostrophe means not. Okay. What's the probability that not E happens? In my Venn diagram on this one, if I was going to draw a Venn diagram, then I would do event E right there in the circle. All right. And then outside of that circle, inside the box, would be not E. Okay. Some of you are going to go, that's not a Venn diagram. Well, it is. It's just not the normal one that we're used to seeing. Okay. Remember, everything inside the box is everything that could happen. So that's one whole. That's 100%. And that would just be the complement of one event. So we're just talking about one thing. Okay. All right. If we go across the page, now we see some. This looks more like the Venn diagram that you're used to seeing. Okay. So we have two events, we have some intersection, things like that. So the first part, the union. The union of two events. Set that contains all the elements that are in at least one or of the two sets, or both. So the key word here for union is or. We have a U right there for union, A union B. All right. And if I was looking at my picture, A union B would be everything inside that figure 8 looking thing there. Okay? Everything inside both circles there. I could be in circle A, circle B, or in both. Okay? So if I asked a question in here, if I said, how many of you are girls and how many of you are juniors or juniors? How many of you are girls or how many are juniors or juniors? Who would raise your hand if it said you're a girl or a junior? All right? Pretty much everybody in the class would do that. All right? Sorry, I left out one. All right? And myself. All right? So that's very inclusive. The or is very inclusive of a lot of that. All right? Now, the intersection. If I go intersection of two events, containing all the elements that are in both sets. So the key word here is and. So if you look here, it's an upside down U, or it's an A without the crossbar, A intersection B. Now if I ask the same question, how many of you are girls and juniors? Now how many hands go up? A lot less, correct? Because in order to raise your hand on that one, you have to do both. You have to be both of those. So the both part is this intersection piece right there. Okay? So we have or, which all I have to do in an or statement is meet one of the requirements. I don't have to meet both. I just have to meet one, and I can raise my hand. In the intersection, I have to meet both requirements to do that. There are quite a few formulas in this unit, all right? The probability of the union of two events, a lot of times we refer to these as combined events. That's how it's going to be referred to on your formula sheet, combined events. And I'm going to modify this formula a little bit because this is only a partial formula. The other part of this is that right there. So the probability of A union B is equal to the probability A plus the probability of B minus the probability A and B. Now, I'll show you why this formula works here in a minute, but that's going to be on our formula page. You'll have it. All right. So, next page. Give you a chance to read this one real quick, and then we're going to discuss. All right. It may be easier off your page than off the screen. All right, so we have 30 students, and we surveyed them, and 17 like to play computer games, 10 of them like to play board games, 9 of them don't play either. It asks us to draw a Venn diagram to show this information, okay? So I'm going to draw me a Venn diagram. So in my Venn diagram, I have this right here. I'm going to say these are my computer game people. These are my board game people. And I'm pretty confident there's probably going to be an overlap. Somebody likes computer games and board games. All right? So I have that there. So I'm going to draw that. What could I place first out of the information that they've given me? The neither. Okay? And so these 9 people right here, they don't play either of these. So these 9 are not going to be in either circle. So they're going to be inside the box, but they're going to be outside the circle. Okay?
Can I have its own circle?
It could, but if I do that, then I'm excluding. If I do a circle there, then I'm saying none of the rest of them work either. All right? So I'm creating another category if I did that. Okay? Now, I'm going to use my formula. Probability of A union B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay? Now in my formula, there's basically 4 variables. All right? Each of these is kind of a variable. What information do I know from the problem? What can I fill in for these variables?
A and B.
I can fill in A and B. All right? I know how many of them play computer games, so I'm going to make that A. All right? There's 17 people that play computer games. There are 10 people that play board games. There's 30 people total. All right? Now, this doesn't include total all the time. All right? Sometimes it might. All right? But this right here, this was everything inside the circles. Well, how many people are inside the circles?
21.
21. Because how many people are inside the box?
30.
30. There's 9 that don't do either type of game. So there's 21 left over that do some form of gaming. All right? So that's the or part. The A or B. All right? Which means I don't know this one. That's the piece. Now, I'm down to 1 variable. That's good. I can solve it. All right? Before I move on, this is the hard part about this problem. All right? If you can understand this, then the rest of it goes pretty easy. Any questions before we move on? All right? So if I add all this up, this is going to be 27 minus x equals 21. I'm going to subtract 27. I'm going to get negative 6 is equal to negative x, which I can make them both positive. So x equals 6. What is x? What does that stand for?
A and B.
Yeah, A and the people that do what? That do both, all right? That's really the piece that I need in this problem. I need to know how many of them do both. There are 6 people that do both, so I'm going to put that in the middle there. Okay? Now, in my purple circle, sorry, I didn't do a very good job drawing that circle. In my purple diagram right here, how many people are in this purple diagram?
17.
17. I've already placed 6 of them, which means how many are left?
11.
11 go there. Okay? In my green circle, how many people are there?
Well, total 10.
Total 10. I've already placed 6, so that means there are 4 left that go there. Now, 4 plus 6 is 10. 11 and 9 is 20. And 10 and 20 is all 30. I got all 30 people accounted for. Okay? Everybody good? Now, at this point in time, now it makes answering the questions a lot easier once I have this. So use your diagram to find the probability that a student chosen at random plays board games.
4 out of 30.
Not quite.
11.
10 out of 30. All right, how many play board games? 10 of them do. All right. Now, it didn't say just board games. It said board games. Okay. And so there's 10 people that play board games. 10 out of 30. Or you could say that is 1/3. Right. Now, some of you, I know what some of you are thinking. Why did I draw the Venn diagram? I could have done that without it. Correct. That one's one I could have done without the Venn diagram. Okay. But I think it's more helpful when I continue going. So part B now. A student plays both computer games and board games.
150.
That's 1/5. Where's that coming from?
6 out of 30.
6 out of 30. By the way, you could leave all these out of 30 if you like. You do not have to reduce them. You can leave them 10 out of 30, 6 out of 30. That is 1/5. All right. Now, that was one I really needed the Venn diagram to help me to find that, or at least the formula to help me to find the piece that's missing. Okay? Now, the very last one, what's the probability that a student plays board games but not computer games?
4 out of 30.
That's the 4. All right? All right? The people that play board games but not computer games, those are those 4 right there. So 4 out of 30 or 2/15. Okay? Questions on that one? We all right? There's a lot of information I could get from that Venn diagram that's very helpful. All right. I think we have to turn the page now, correct? Yes. All right, we're going to do another one of these. All right. I think this one's helpful because it helps you kind of see where this formula is coming from. All right. Got that same formula, probability A union B is equal to probability A plus probability B minus the probability of A and B. Now, some of you have an idea about cards, and some of you cards are kind of a foreign thing, all right? So there are 52 playing cards in a deck of cards, all right? How can they be categorized? In suits. We can do it in suits. What are the suits? Spades, diamonds, clubs, hearts. All right, so 2 black suits and 2 red suits. All right, in each suit there is an ace, which I count as out of 1. All right, a 2, 3, 4, 5, 6, 7, 8, 9, 10, and then there's a jack, king, and queen. So there's 13 in each suit. All right, so there's 13 hearts, 13 spades, 13 diamonds, 13 clubs. All right. The other way we could categorize it is we could talk about the value of the card. There are 4 aces. There are 4 kings. There are 4 queens. There are 4 sevens. All right? So we can do that. So on this one, a card is drawn at random from an ordinary pack of 52 playing cards. Find the probability that the card is a heart or a king, which it's asking for this right here. That's the or part. So what's the probability that I'm a heart or a king? That's what it's asking. So if I do the first one, what is the probability of a heart?
What's a 4th 52?
Say again?
What's a 4th of 52?
A 4th of 52?
That'd be 13.
That'd be 13.
Oh, 13.
So there are 13 hearts. Basically, like I was saying a while ago, your ace is 1 through 10, so that's 10 of them, and jack, king, queen, so there's 13. All right? So 13 out of 52. Now, we could reduce that to 1/4 because there's 4 different suits. All right? But I'm going to leave it like that for now. All right? What is the probability of drawing a king? 4 over 52. There's 4 kings. King of heart, king of spades, king of diamonds, king of clubs. All right? There are 4 out of 52. Now, you're right. That's 1 out of 13 if you'd like to reduce it. I'm going to leave it right there because what am I doing? I'm adding those together, correct? Now, many people right now will add that together. They're going to say the probability is 17 out of 52. There's one problem with that. What's the problem? The whole other part of the equation. And what is that whole other part of the equation talking about? What happened here? I counted the king of hearts here. I also counted the king of hearts here. So I double counted the king of hearts. Make sense? And so this last little piece of this is taking care of all that double counting. All right? We want to make sure that we don't double count something and over estimate. All right? So how many king of hearts are there?
Or one.
There's just one. There's only one card that got double counted. So minus the 1 out of 52. So this is kind of where that problem, that situation is where this equation kind of arose from. All right? So that was 17 minus 1. So this would be 16 out of 52. Perfectly fine with that answer. If that bothers you, there's a 4 that goes into both of those. And 4 out of 13 would be the answer there. Okay? So you see with the cards kind of how that formula gets created. All right? I can't double count.
You're not gonna put anything with cards.
Huh?
You're not gonna put anything with cards on.
If I put something with cards, I'm either I'll help you through it, or they have. I've seen it on the actual IB test before, but they put out they put a picture of the whole deck. All right, so you can see it, and then like you can count it or whatever. So that, because I think they understand too that cards is not something that like everybody worldwide does and stuff, and so you got to be careful with putting that. Okay, all right, but it gets used a lot in probability. All right. Take a look at this one. They like to put little problems like this. I'll give you a chance to look at it. Many people don't like this one because there's no backstory to it. All right, and so I have probability of A, I have probability of B. They gave me both of those. Then they mentioned probability of A union B and probability of A and B. All right, so because of the nature of this, I probably would use this formula right here. So this is the same formula that we've been discussing. So I'm going to use that formula. Okay? Again, there's 4 variables. What could I put into this equation? I can put in A and B. I know A is 9/20. I know B is 3/10. All right? But now I'm a little bit stuck here. We could change this and add them, but I still need to know these two first before going. You're right. I'm gonna address that in here in a second.
Couldn't you just
Okay.
put X into that?
Okay. And so I need a variable. I don't know either one of those. And so you're right. How are these things connected? This one right here is worth 2 of these right here. So the way that I would probably do that is I would make this one X. The probability of A union B, A intersection B, I would make that one X, which means if I'm going to go find this one, then it's going to be 2X. Now, why wouldn't I have used Y and X?
Because they're related, so it's like.
They're related, so I can kind of keep them together. If I use Y and X, then I got 2 different variables. Now I'm having to solve for 2 variables. I just want to solve for 1 variable. And since they're connected, this is a pretty easy way to do that. Okay? Before I move on, this is the most difficult part of this problem, is getting here. All right? If we get here, then the rest of it kind of falls in place pretty easy. All right? Any questions? I would probably add the X and add the X. So I have 3X. And then, like you said, I'm going to have to put these together some way. There's 2 ways I think you can go about putting those together. Then they mentioned that we can multiply by 2 and multiply by 2. So we would have 6/20 and 9/20, which would be 15/20. That's one way to do it. Okay? Or some of you going, I don't want to deal with fractions, and you might say this is 0.45. That's what 9 divided by 20 is. This is 3/10, which is just 0.3. That's 3/10. And I can add that together, and I could say that that is 0.75. I don't care. You could use decimals. You could use fractions. Now, to tell you the truth, Which of these would you rather divide by 3?
The fraction.
You'd rather divide the fraction by 3?
I mean,
I'd rather take 75 cents and divide it by 3. Because that would be a quarter, right? Alright.
The other one's really just.
The other one's not bad.
Very easy.
It's easy too, alright? Or it's not awful. And so, but I'm gonna divide by 3. Divide by 3, so x is gonna equal to, 0.25, or you would have gotten 5/20ths, which is the same thing as 1/4. Okay? So this is x. You could have gotten any of those answers. I would have accepted any of those. Okay? Now, let's go into the problem. Part A says, what's the probability of A union B? Do we have the answer?
That times 2.
This times 2. We found the answer for this. Alright, that was x, but we need to find the answer for that, which is double that. So if I double a quarter,
50.
then it's 50. Okay? And so that is correct. So this is 0.5, or you could tell me 1/2, either way. Okay? Part B. Somebody read that for me. That is the probability of what?
The not.
Not A or B. Yeah,
And then
this is the
also-
probability of not A or B. So if this is the probability of A or B, this is the probability of not A or B, so what would it be?
1/2.
Also 1/2. Because 1/2 is everything. Probability of A or B is here, it's 50% basically. The probability of not being A or B is 50% as well. Okay? So this is 0.5 or 1/2. Now, let me do this real quick. Before I get to this last one, I think the Venn diagram is going to help kind of pull all of this together for me. All right? So if I were to do a Venn diagram, I have A here, and I have B here. And the first thing that we did is we found this right here, which was the intersection. So this is 0.25 that goes there. All right? You could do it in fractions as well if you like. All right? If this is A and this is B, then the probability of B was 3/10, or it was 0.3. Well, if 0.3 goes in the blue circle, and I've already put 0.25, then what's left? 0.05. That adds up to 0.3. If A is 9/20ths, but we said it was 0.45, if I already assigned 0.25, then this is 0.20. Okay? If I added all of that up, which that's what answer A is, that's 0.5. That's a half. Okay? Now, the probability of not being in the figure 8, that's everything in the box, but outside the circles, that is 0.5. 0.5 would go there. Okay? Now, for part C, somebody read part C. How would you read that? Probability of?
Not A or B.
Not quite.
Probability of
And
not
B.
A and not B. The probability of A and not B. Probability that I'm in the circle for A and I'm not in the circle for B.
So you can do the little thing on like outside the parentheses or on
Well,
each individual.
this outside the parentheses
is
there is applying to that whole thing.
Right, so but you could do it on any
Yes,
individual.
so I could do it on an individual one as well.
We're not gonna be touching De Morgan's laws, right? Cause I don't like those.
Touch what?
Oh, never mind. Okay, that's like the statement that's like, this or this is equal to not parentheses, not
No, I don't
that,
think we're doing all that
or
logic.
not that.
We'll do a
that,
little bit more
like
of this,
we did
but
that.
not quite that extent. No.
Okay.
All right. Now, the probability of in circle A, so I need to be in circle A, so I need to be in the red circle, but I don't want to be in circle B. So I don't want that part. So this is the part that I want. That's the part that's in circle A and not in circle B. So 0.2, or you could say 1/5 if you wanted to do a fraction. Okay? That's the part that's not there. Good? That part, question C, that would be very difficult to answer without a picture. Okay? All right. We've got one more last little thing, and one problem to go along with it. All right? What's the word exclusive? alone, together, by itself kind of deal. I didn't know that when I was a little bit older than you. I went to a party one time with my now wife, but somebody asked me, hey, are y'all exclusive? I was like, no, we're not exclusive. Didn't really know what that meant. That was not a good thing, all right? Because being exclusive means that you're together and you're nobody else, all right? I didn't know that, so that was a really embarrassing thing. My wife is very good with words, and so she knew all that. So that was not a good thing. I had to dig out of that hole a little bit. But mutually exclusive, all right? They are by themselves, all right? They are not overlapping. And so a Venn diagram there would be the A right there and the B right there, and there would not be any overlap. They're exclusive, all right? They're self-contained, basically, so as you go, okay? So that would be a Venn diagram for a mutually exclusive event. They cannot happen at the same time, all right? If I were to give you a die, if I were to give you this die and say, hey, I want you to roll me an even number and an odd number at the same time. You can't do that, right? Those are mutually exclusive events. You can roll an even number, or you can roll an odd number, but you can't do both of those at the same time, all right? And so that would be an example of mutually exclusive, all right? Now, if I'm talking about the probability, this formula right here is on your formula page. The probability of A plus the probability of B equals the probability of A or B here. Since there's no overlap, it's a simple addition. Take whatever's in this circle, take what's in that circle, add them together, and that would be the probability of A or B. Okay? The other thing about this is the intersection doesn't exist. All right? There is no overlap here. So the probability of A and B would be nothing. It'd be 0. Okay? So let's do one of these questions. So next problem on your page. Give you a chance to read it. And I want you to see if you could draw me the Venn diagram. So it says we have a box that contains a lot of different colors of pens in it. Teacher picks out a pen at random. The probability of drawing out a red pen would be 1/5. The probability of drawing out a green pen would be 3/7. All right, and then it's asked me what's the probability of drawing neither. So we'll get to that here in a second. Questions about my Venn diagram. Is this a mutually exclusive event? Can you draw a red-green pen? That sounds silly even saying it, right? All right. You can't do that. So on this one, what's the probability of drawing a red or green pen? What would we do?
1/5 plus 3.
1/5 plus 3/7. Okay? So I'm going to go 1/5 plus 3/7. How would I do that?
Find a common denominator.
Need to find a common denominator. What would be a common denominator?
35.
35. The 5 and the 7. So multiply the other one by the other denominator. So multiply that one by 7. Multiply this one by 5. So 7/35 plus 15/35 would be 22/35. What's that?
A.
That's the probability of either.
Either. That's probably of a red one or a green one. Okay? Well, what is it that we're wanting?
Neither.
Neither one of those. So how do I do that?
What's left?
Subtract it from what? Subtract from 1. So basically in the diagram what I'm wanting is I'm wanting everything in the box but not in the circles. I want this. Alright? And so I'm going to take 1, which is everything, minus the part that I don't want. So I don't want the 22 35ths. Now we'll get that. Now, how else could I represent 1?
35 over 35.
Thank you. 35 over 35
You're good.
minus 22 over 35 equals 13 over 35. Okay? All right, we're going to end there today. We've got about 3 or 4 minutes left on your homework page. We have page 368, 370, and 371. What I'd like for you to do is I want you to mark on that. I want you to mark them all as odds. I want you to do the odds for all those. Okay?
So we do the Tuesday one.
So do Tuesday, all right? We'll check those on Thursday, all right? I won't stamp on tomorrow, all right? But we'll go over those on Thursday. But shorten it a little bit. It's not quite in half, but it's close, all right? So you're doing the odds on those pages. 368, 370, and 371.